Hi, welcome to Programming Foundations for Machine Learning. In today's lecture, we will be looking at NumPy. Even if you have spent very little time on machine learning or in data science, I'm pretty sure you would have heard of NumPy. If you have never heard of it, this is the first time you are hearing about NumPy, don't worry. We'll anyway be treating NumPy in today's lecture as a complete beginner. So this lecture has 4 objectives. At the end of today's lecture, first of all, we will do a small recap of Python fundamentals, its syntax, data types, etc. I will not be spending too much time, but I'll provide you a couple of links which will help you to cover basic Python syntax. But in any case, for the sake of completeness, I will do initially a small, quick Python syntax recap. Then we will be discussing what is NumPy, how do you use it in the context of handling data. We will also discuss why NumPy was so foundational in data science and machine learning when it was introduced. And we will also do some hands-on exercises that will give you a very good familiarity with using NumPy. All of this will be coded. We will be using Google Colab for implementing this code in Python. So let us have a quick recap on Python itself, basics of Python. Python is a very easy to learn, readable, easy to understand syntax programming language. It is by far the most popular programming language for machine learning and data science. I'm pretty sure you already know this. One of the reasons why Python gained so much popularity is because there are so many libraries which have been developed in Python over the course of last maybe 20 plus years, which makes machine learning implementation so friendly. So the community support in Python is also very, very good, unlike any other programming language for ML or DS. So these are the reasons why we are talking about Python today, specifically in the context of machine learning. So some of the data types that Python has, int, integer, float is floating point numbers like 2.3, numbers with decimal points, string, boolean like true or false, and list. We'll be spending a little bit of time in Python lists today because we will be discussing why NumPy was superior for performing array operations compared to the Python lists. Then there are conditional statements and loops. So if else condition, for loops, while loops, etc. We can implement a very basic code today before we proceed with NumPy. And of course, we can define functions with this code block called def, and these functions can be called from anywhere so that you don't have to write the code again and again and again. So I have written a sample code here just to print hello with your name. So what I'm going to do is, let us go to Google Colab. So open colab.research.google.com, and this will ask you to either open an existing notebook or open a new Google Colab notebook. I'm going to open a new Google Colab notebook. So here, what we will do is, once this loads, let me rename this as intro to NumPy. Although the very first code that we are going to be writing has nothing to do with NumPy. It's this function. So define print your name, and then we are passing name into this function. And let's say print your name is name. Also, let me zoom in a little bit so that you can see better. So we have to add an F because here is a variable. And then we call the function from outside. So we can call it by using the function name. Name is print your name. And I'm passing my name, and it prints my name. So this is a function for printing this variable in Python. And we can also do something like print. Let's say I am returning. So if instead of printing, I can just return some value. So return this, right? So we can attribute whatever the function is returning into some variable. So let's say function result equal to this. So now whatever is the output from the function will be stored in this variable. And we can print something like, so first let me print the value of the variable itself. So that will be this, whatever this is, because that is the returned value, right? So function returns this string and that is stored in this, and then we are printing it. And then we can print type of this variable, and hopefully it should be string. So you can see that it's a string data type. Similarly, let's say I have two more, name, age, height, and then here I return something like your name is this, age is age, and height is height. What we can do is here we can print the data type of age is, then we say type of age, and this we can put in F, and the data type of height is type of height, the data type of name is type of name. So this is just to print the type data type, and you are just returning age is this, height is this, name is this. And what we do is we can simply print the function result because data type is printed inside the function. So here what we need to do is we have to pass three things, right? The name, age, and height, 175.5, something like this, centimeter. And here, let's say full name. And now if we run the function, you can see that the data type of age is integer, height data type is float, name data type is string, and your name is Sridhar Panat, age is 31, and height is 175.5 centimeter. Very basic execution of a Python code, which also deals with three different popular data types. One more data type that I want to show you today is list in Python. So let's say there is one more thing, data type called marks, and here print your marks. The data type marks is type of marks, and we can do this. And then what we do is let us pass the marks. So marks we can pass, let's say there are three subjects, so 31, 42, and 27, something like this. And then here, let us not print this. Maybe we can do, and your marks are marks. Let's see, right? So now this is a Python list because you have a set of numbers. Let's see now what is the output. So the data type of marks is now its data type is list, and your marks are 31, 42, 27. So you are outputting the three numbers. We can also do something like marks of 0, that's the first element, marks of 1, and then marks of 2, so that you don't need the brackets. So your marks are 31, 42, 27. So that's this is about different data types in Python. And now let us go back to the lecture note, and there is a quick exercise. Print all even numbers from 1 to 10 using a loop. So we can use a for loop, and we can divide the number by 2 to see if it's an even or odd. If there is a remainder, it's a even number, I mean odd number, otherwise it's an even number, right? So for I in a range of 10, and what do we have to do? We have to print if I mod 2. I mod 2 means it's a remainder what you have after dividing I by 2. Print if this is equal to 0, then it's an even number. Then the current, or let's just print I. So we'll just print I, and That's it, right? So for I in range of 10, if I mod 2 equal to 0, print I. So 0, 2, 4, 6, 8. So we were asked to print from 1 to 10 actually. So what we should do is for I in range of 10, if I mod 2, so or rather I plus 1 mod 2 equal to 0, print I plus 1. Now this I will go from 0 to 9, then I plus 1 will go from 1 to 10. And then we are checking if I plus 1 is divisible by 2 or not. Now hopefully it should print, yeah. So 2, 4, 6, 8, 10. So this is a function which uses, not a function, this is a for loop inside which we have an if condition also. And we can wrap this whole thing inside a function. So define, let's say even number printer. And then here, let's say we want to print the even numbers from 1 to n. Then all we need to do is like change this to n and provide an indentation. And then here we should have a colon. And we just call the function with whatever even number whatever number up till we want to print the number of all the even numbers. So let's say we want to print all the even numbers from 1 to 50. We call the function with 50 as the input. So now if we run, it should print 2, 4, 6, 8, 10 like that up to 50, right? So this is a small piece of code which deals with numbers, small mathematical operation, functions, for loops, and if condition statement, and also output. Printing is an output. So very, very easy thing to do. Please try this out yourself, right? It's easy for you to watch. The code is, by the way, very easy, nothing complicated at all, but just do it yourself without looking at the screen. Just do it from scratch in Colab. I'm pretty sure you will get a better feel for it. All right. So now let us come to the main thing. What is NumPy? NumPy is the main thing that we are learning today. Before NumPy was used, actually, Python lists, which I just showed you, the square bracket inside that you have a list of numbers separated by comma. That is what was used for handling a set of numeric data. But this was not very efficient. Python lists had a lot of problems, which we will see in the rest of today's lecture. And if you had to conduct operations like vector dot product or matrix multiplication, etc., you had to use for loops, because if you are doing element wise dot product, you have to take the first element of both arrays, then multiply them, then take the second element, multiply them, and then add all of them together. So all of this had to be done using for loop. So this was very inefficient because in linear algebra, in machine learning, you are almost always dealing with matrices of multiple dimensions. So you will have a set of numbers to deal with always, and you will have to perform mathematical operations on these numbers. So it will be so inefficient if you are doing it one number at a time using some for loop. So this is an example of how you would be doing your operations in Python if you had just Python lists, no NumPy, right? So let us write the code from scratch and just implement a code for doing element-wise dot product. So let's say A is a list with numbers 1, 2, 3. And B is another list with numbers 4, 5, 6. Now element-wise dot product should be 1 times 4 plus 2 times 5 plus 6 times 3. So 18 plus 10, 28. 28 plus 4, 32. This should be the answer. So let's say for I in range of length of A, then you can have one more for loop for J in range. Actually, J is not needed. Then all we need to do is, and let's say sum initially, we initiate the sum to be 0. Sum equal to sum plus A of I multiplied by B of I. So this is how you can calculate the sum, and then we say print the sum is sum. So here you can see the sum is 32, right? But this is very inefficient because these arrays were just, these lists were just 3 numbers. So what if they had 1 million numbers each? The calculation will take much longer because you are doing one calculation at a time. So for loop is executing one calculation after the next. So this is a very, very inefficient way to do these things. By the way, this can be written just like sum plus equal to. This is a shorthand notation to do the same exact operation. Sum is 32, right? So this is a big disadvantage by just using Python lists. These lists are slow. I will show you how slow these are in comparison to NumPy soon. We can do a calculation on very big matrices or arrays, and let's see how fast NumPy can execute the same operation compared to Python lists. They are memory inefficient. You are not vectorizing the operation. So here, although technically you have two vectors, you are treating them as individual numbers because you are using it element wise. So the fact that you have vectors, you are not utilizing it. And what is the advantage of vectors here? Because you should be ideally be able to do parallel calculations, because if you are multiplying 1 and 4, the product is 4, 2 and 5, the product is 10. So you could technically do the product of 2 and 5 and 1 and 4 at the same time. There is nothing that is dependent here. So the first two products, first pair of product is not dependent on the second pair. It's not dependent on the third pair. The total sum is, of course, you have to store it somewhere. So total sum depends on these individual numbers, but the individual multiplication itself is not dependent. So we are not utilizing the way in which CPU can execute certain computations fast. So operations like matrix multiplication or broadcasting. So broadcasting here, what it means is if you have an array and if you want to multiply every single element in this array with just one number, again, you have to do it element wise here. So it's very, very inefficient way to do this. So what NumPy did is NumPy changed everything with respect to Python list calculations. It was introduced in the early 2000s. And one thing I want to mention is that NumPy, although it's a Python library, most of its code is written in C or C++. So, that I have just put here. This meme I have seen many places on Reddit and many other places on internet. But basically, many Python libraries actually involve tremendous amount of C or C++ code. So one of the claims of NumPy is that it is as easy to use as Python because it's a Python library. You can call it with just one line of code, but it is almost as fast as code that is written in C or C++. So that is what is NumPy. And NumPy basically allows you to define multi-dimensional arrays. So multi-dimensional array is effectively like a list of lists. So if you wanted to convert this into a two-dimensional array in Python, maybe you can define something like this. So the first list is 1, 2, 3. Second list is 4, 5, 6. So this is a list of list. But at the end of the day, the data type of C is also list. Okay. So, but NumPy makes it even more efficient to do all these things. So we will see that. Then we can perform calculations without having these for loops. We don't have to perform element-wise calculations. If you want to multiply all the elements of an array with just a number like 2 or 1.5, you can do that using broadcasting. And NumPy also laid the foundation for pandas, scikit-learn, and the early versions of TensorFlow, etc. Although TensorFlow is much better than NumPy because TensorFlow can allow you to use GPU, whereas NumPy is primarily based on CPU. But that's anyway a different topic altogether. But NumPy laid the foundations for most of the modern things that we see in machine learning today. And there is even a saying that if you really know NumPy, you know half of machine learning in terms of implementation. So it's an amazing library, and we'll be using it today and also in the rest of our machine learning journey. So let's see how we can use NumPy, how to import the NumPy library. You may have seen in many machine learning codes a statement like import NumPy as NP. So this means you are using NumPy, but you're calling it as NP. So we can do the same thing here. Import NumPy as NP. And here in this code, what we are defining is we are defining two types of arrays. First one is a 1D array. It has just one dimension. The other one is almost like a list of lists, but this list of lists is being converted into a NumPy array by calling the array function from NP. So we can write this in the following way: a equal to okay, first let me do this. Let me copy paste this, and then a equal to np dot array of this guy, okay, and b equal to np dot array of the value of b. Similarly, c equal to np dot array of, we had defined c here. I'll copy that and paste it here. And if we run this, basically a, b, c NumPy arrays are defined. Here np can be replaced with whatever, and we can use that. So xy, xy, xy. See, that also works. Or we can also call NumPy.array, NumPy.array, NumPy.array. This also works. Oh, this also works. So, so all of these are valid, but the most common usage of NumPy is, instead of NumPy, just use NP, because it's easier to type. Otherwise, how many times will you type NumPy, NumPy? So this is how you define a NumPy array. And oh, sorry, this should be NP. And here, the first guy is of 1 dimension, second guy is of 2 dimensions. Same in our example. Now, we can perform an operation called broadcasting. So let us first do that. A equal to a multiplied by 2. So what happens here? If we print a, you can see that all the elements in a got multiplied by the number 2. So this became 2, 4, 6. What if we had just a list? So let's say D is a list called 1, 2, 3. Okay. And then here we are saying D equal to D multiplied by 2. Then print A, print D. So here what you can see is D was a list. This list did not get element wise multiplied individually. Instead, the D, like the list has doubled in length. If this was 3, basically you will have the same list repeating 3 times. So it's increasing in its size instead of individual elements being multiplied by that number. Whereas for A, it is getting multiplied by whatever number we are multiplying it with. So this is the main difference between NumPy and Python lists. NumPy allows you to do an operation called as broadcasting. You can influence all the elements in the array with just one calculation, with just one operation. Then yeah, this is element-wise multiplication. What we saw here was element-wise. This was element-wise multiplication. Let me also do element-wise addition. B equal to B plus 2. And let me also print B. So here B is actually 4, 5, 6. I wanted to do C, not B. That's the 2-dimensional one. So print C. So C was 1, 2, 3, 4, 5, 6. Then now it will become 3, 4, 5, 6, 7, 8. So you are adding 2 to all the elements in the C array. So this is the element-wise operation, like matrix multiplication. Sorry, not matrix multiplication, element-wise multiplication or element-wise addition using NumPy arrays. This is an example of a built-in function in NumPy for finding square root. So np.sqrt of let's say C should give you. And if I'm removing this print statement, this should give me the square root of 1, square root of 2, square root of 3, square root of 4 should be 2. Square root of 1 should be, I'm doing C is equal to C plus 2, right? So let me just, So square root of 1 is 1, square root of 2 is 1.414, like that. So you're getting the square root. And what else can we do? Maybe np.log of C. And log 1 should be 0. And if there was log, is there np.e? Let's see. Yeah, so np.e is, so this log is basically the natural logarithm. So np.e is the value of e. It's 2.718 or something, right? This is, or 3 value of e. 2.718. So this np.e, if we print np.e, should be that number 2.718. And the natural logarithm of this should be 1. Natural logarithm of 1 should be 0, because any number raised to 0 is 1, and e raised to 1 is e. So when you're taking natural log, that's what's happening. You can also take log to the base 10. So if we do log np.log 10 of c, this guy will become 0, this guy will become 1, because log 10 of 10 is 1. So here you can see that 10 has become 1, 1 has become 0. So all these operations are inbuilt, defined inside the NumPy library, which makes it very easy for you to perform all these calculations. So this is one of the biggest advantages of using NumPy over Python lists or any other packages for mathematical operations using these arrays. Next is indexing and slicing operation in NumPy. So if we want to access just one element, one specific element, let me remove all of this. So if we want to print the first element in A, it's A of 0. This should print 1. So indexing starts from 0, not from 1. And the last index here should be 2. But if we try to print A of 3 does not exist. So there is an index error, because A of 3 is not, it's out of bounds. The length of A is 3, which means index goes from 0 to 2. A of 2 will be 3. Similarly, this C has 2 dimensions, right? So if I want to print the first element of C, if I just do C of 0, what happens is, this is a list of list. So C of 0 is the first list inside this list of lists, right? So this is sort of like a list of list. First element is this guy. Sorry, first element meaning 0th element as the 0th index. Element at the first index is this guy. So if I just ask to print C of 0, this whole list will be printed. C of 1 means this whole list will be printed. So how do I access, let's say, the first element inside the first list? I can do C of 0 of 0. So now this is this. C of 0 of 1 is this. C of 0 of 2 is this. Right? So this is how you go along the first lists, along the set of elements in the first list. Then what else? Yeah, you could also do this 0, 2. C of 0, 2 means that's also 3. C of 0, 0 means that will be this guy. Let's also do this, no? Let's print type of this. Type of C of 0, 0 is numpy.in64. Type of 0 of 0, C of 0 of 0. That is also numpy.in64. So the type is 64-bit integer. Okay, so that is pretty much it about indexing. Now reshaping. So NumPy will allow you to reshape a particular list. So what we can do is, let us create D equal to 1, 2, 3, 4, 5, 6. That's it, 6 elements. Okay. So if we normally print D, it should print all this, and D.shape. Oh, D is not a NumPy, so np.array of this. Now it's a NumPy array, and D.shape should be 6. So it's a it is a one-dimensional array which has 6 elements. We can also make this into a 2-dimensional array. We just need to make it like a list of lists inside the bracket. So there is one square bracket, and inside that there is another list. So this is a list of lists, and this one will have a shape of there is one list inside the list, and that list has 6 elements. So 1, 6. Now let's go back to the previous configuration. We can also do something like reshaping the dimension of this array. So let's say D equal to np.reshape. So currently the shape is 1 dimensions and 6 elements. Let us do the np.reshape of D, and there are 6 elements, right? So we can reshape this into 2, 3. And if we print D, this will be, there are 2 lists inside the list. First one has 3 items and second one has 3 items. And if we print D.shape, this should print 2, 3. So we are converting. But if we give this as 2, 4, there is a value error because you have only 6 elements available. 2, 4 means you are expecting 8 elements. So that will not work. So 2, 3 will give you this. 1, 2, 3 will be the first row. 4, 5, 6 will be the second. 3, 2 means 1, 2, 3, 4 and 5, 6. So here you can see that. So this is the np.reshape command. You can also calculate the sum along a particular row or particular column. So that is the next part. So here what we are doing is in the array, we are summing along the 0th axis. 0th axis mean column, and axis equal to 1 means you are summing or taking mean or performing a mathematical operation along a row. So what we can do is print np.sum of what we can do is d comma axis equal to 0. So if axis is 0, so first of all, let me remove this part and I'll convert this into a 2-dimensional array with list inside list. So there are 2 lists. 1, 2, 3 is the first list. 4, 5, 6 is the second list. That is inside the main list, and that we are converting into the NP array. Now what we are doing is we are performing a sum of this D along axis 0. Axis 0 means column, right? So the first column has elements 1 and 4. So sum will be 5. Second column has 2 and 5. Sum is 7. Third has 3 and 6. And here, if we put axis equal to 1, you will have a sum along the rows. So first row has 1, 2, 3. So sum is 6. Second has 6, 4, 5, 6. So it will be 6 plus 4, 10, 10 plus 5, 15. So this is the np.sum. You can also calculate np.mean. np.mean along axis equal to 1 should be 5. So let's, for this one, it should be 5. And for this one, it should be 2, the middle number. If we are calculating along axis 0, mean should be 2.5, 3.5 and 4.5. Because it will be the mean of 1 plus 4, mean of 1 and 4, mean of 2 and 5, and mean of 3 and 6. So that is these are the mathematical operations which we can apply along rows or along columns in a NumPy array. Okay, so that is reshaping and aggregation, as in aggregating the values to calculate the sum or calculate the mean or any other mathematical number. Now let us actually talk a little bit about the real difference between Python lists and NumPy arrays. So we were saying NumPy arrays have really changed the way in which we implement mathematical operations to these lists, right? So Python lists are slow. We said that, but we did not experiment with certain numbers. NumPy arrays are fast. So here I have listed 2 examples. So first example is we multiply 2 arrays simply element wise. So 1-to-1 mapping, element wise we multiply, but the number of elements are 1 million. So it's a very, very big array. So what we do is we have 2 blocks of code here. In the first part here, we perform the element wise multiplication using Python list. So the first list is a list who has n number of items, and these items are, list 1 is 1 million such items, list 2 is again 1 million items, and then here start equal to time will note the starting time, and immediately after the calculation is done, you are noting the ending time, and then we print the result. And then here again we do the same thing, but this time instead of list we use an array. So let us implement this code from scratch. I have written the code here, but let's do it from scratch. So import NumPy as np, import time. Now let's say we want to write the code for first doing the calculation using Python lists. And what we do is, okay, I have already gotten a code, but I will not be using NumPy. So what I'm going to use is just let us have 2 lists, list of range of n, and we have to define that n is the number of elements, n equal to 1 million, 100,000 million. So to make this easy to read, we can put something like underscore. So we know that, I mean, this is same as 1 million. Python will ignore these underscores, but it's easy that way to read these big numbers. So this is 1 million. And A is the first list and B is the second list, and that should also be list of range of n. Okay. Now what we do is, if we want to do element wise multiplication, we can do for I in range of length of A. What we do is we can also do something like C equal to list of 0 multiplied by range of n, and C of I equal to A of I multiplied by B of I, and that's it. So here unsupported int and range. So what we should do is, first let me create this C with some default values, no problem. And okay, so here is the calculation, right? So time equal to time dot start. This I can define time dot start, and time end equal to time dot end, and print the total time taken equal to time end minus time start. So this can be time end minus time start. Time has no attribute start, so let's see, it should be simply time. So you're just noting the time, right? And then you are simply subtracting them. Total time taken is 0.216 seconds. Then what we can do is, we can do the same thing, but this time using NumPy. So maybe I can write it in the same block. So now you have A, you have B, and you have C. So D, this time A equal to np dot a range of n, B equal to np dot a range of n, and C equal to, I can define the same thing, but then it won't matter. C will be, and then I'll say, actually I don't need this. I can just say C equal to A multiplied by B, or I can do np dot dot of A comma B, and here I should define the time start with np equal to time dot time, and time end with np equal to time dot time. Total time taken with NumPy, and this is total time taken with lists, equal to time end np minus time start np. And let me delete this, I should have here. So NumPy dot has taken significantly lesser time. You can see this. Let's also just print the shape of C equal to np dot shape. Then here I can say the length of C equal to len of C. Obviously this should be 1 million, and here maybe I'll rename this as D, and the shape of D. Okay, so function shape equal to np dot shape of D. The shape of D equal to np dot dot of A comma B. Oh, np dot, it should not be np dot dot, it should simply be A multiplied by B. Yeah, because NP dot dot means you are taking the element wise sum, but also the element wise product and also the sum of those. It's like the dot product. So it should be A multiplied by B. So you can see the difference. This took 0.184 seconds. This one took 0.0023 seconds. If I had 10 million instead of 1 million, this difference will be even more stark difference. So 1.88 seconds versus 0.045 seconds. So it's very, very much different what NumPy can do versus what Python list can do. NumPy is definitely much more efficient. So here, and the reason why that's happening is because you are performing parallel calculations here. So A times B means element wise it's doing the multiplication all at once. So one thing you should notice, so this is 0.045, right? So now let's keep it 1 million. How much was that? That was also 0.004. So okay, it has decreased by an order of magnitude, but still it's still much faster than what Python list can do. So this is an example of what you can accomplish using arrays, NumPy arrays compared to Python lists. I have one more example here which we can do, multiplying two matrices of dimension 100 by 100. So let us do that also, and let's see what's the difference between the calculation done using NumPy versus using Python lists. So the ultimate conclusion here should be, for dealing with matrices, especially when you are having CPU, NumPy is better. But if you have GPU access, TensorFlow would be better. But we are not going into that in this lecture. Let's keep it simple. TensorFlow allows you to make parallel computation much easier in presence of GPU. So usually it's better to define these arrays as TensorFlow objects instead of NumPy arrays. But currently, let's say for normal people who do not have access to GPU, NumPy is still the best option. So we can implement this code pretty much from scratch. It's fairly straightforward. So let us again, we don't have to import NumPy again because it's already imported up here. But anyways, for the sake of completeness, let's do that as NP and then import time. And then what we do is n equal to 100. So we are going to define two matrices of size 100 by 100. So first we need a for loop for I in range of 100 and for j in range of 100. And here we can define a matrix A, list of list A of I of j equal to random number. So we can import random. So import random. Then we say matrix, or let's say the starting time, we can call it as time to start equal to time dot time. And then we create A. Then actually starting should not be here, but we'll change it. This is A for I in range of 100, and this is B. And C we can define as a matrix with just zeros, and then later we can replace the values in C. And C of I comma j is 0. So C is just a matrix with bunch of zeros. So that is ABC. Oh, this should be J. And J, this should be, let's keep this as N so that this will be variable. This should be N. All right. Let me save this once. Yeah. Okay, this should be capital C. And then what we do is, for matrix multiplication, what we need is, we are multiplying the first row of the first array, first matrix, with the first column of the first of the second matrix, right? So for I in range of n, for j in range of n, for k in range of n also, because it's technically not needed, but we will have to go through the first matrix along the row and along the column, and second matrix along the column. C of I comma j plus equal to A of I comma k multiplied by B of k comma j. This is fine. And time start we should bring here, not the place where we define A and B, but over here. Okay, so time start, time end, total time taken equal to time end minus time start. Hopefully this works. Let's see. List index is out of range. So A of I of j. What we can do here to fix this error is we can just append. So for I in range of n, we can simply do a dot append 0. So a list with just 0, but then multiply by n. So this we have just seen before, right? So 0 multiplied by n. If a list is multiplied by n, the list will become n elements of this value. Then b dot append of zeros, a list of zeros multiplied by n, and we can do the same thing for c. And this should hopefully fix the issue of index out of bounds. C is this. Okay. Yeah, I hope now the code should work. Okay. So the total time taken for this is 0.245. Okay. Now what we do is we define using NumPy. So a equal to np dot random dot rand of n comma n. So this will be a array with n by n dimension, and it should be random numbers. B equal to np dot random dot rand of n comma n. If we want to combine these two codes so that with one run, if we want to get the output, what we can do is here I can call this as A1 and B1. And then we say C1 equal to, there is an easy way to do multiplication, A1 at B1. So this will perform matrix multiplication. And before we do this, we do time start np equal to time dot time, time end np equal to time dot time, C1. So here what I did is Gemini provided me suggestion, so I just accepted it because it's anyway easy. So here we say time total time taken with NumPy, total time taken with this is with Python lists equal to. So that's it, right? So let's run the code and see what happens. So total time taken with Python lists is 0.257 seconds. With NumPy, it's 0.016 seconds. Very, very fast. What if this size was 1000 instead of 100? We'll see. The difference will be even more dramatic. So this at this function, where is that? Oh, here they suggested matmul, but we can replace it with at, which should perform the same thing. So the 1000 by 1000 execution was taking a bit of time. So I have for now paused it because it's affecting my video recording as well, because it's causing my video recording to slow down. So let's keep it at 100 by 100. This np.matmul actually we can replace, as I showed you earlier, with just A1 at B1. Oops. This should give the same result. So this is also same as performing matrix multiplication. What can we do to show the dimension, output dimension? Print C1 dot shape. So this should be 100 by 100. Over here, if we print len of C, len of C will be 100. But what if we print len of C, comma So len of c means number of lists, and then len of c of 0. So c of 0 is the first list in the list of lists. So that should also be 100. So it's 100, 100. So every list is 100 in length. So you can see that you multiply two matrices 100 by 100, you get 100 by 100 matrix as the result. And in one case, when you just use Python list, you're using for loops, very slow. 0.245 seconds is not slow, but imagine doing this with very, very big matrices for machine learning applications. This whole thing will be completely slow. And you can see NumPy is much faster. So this is truly the effect of converting calculations into a vectorized format. So literally NumPy, when it was introduced for the first time, it truly revolutionized the way machine learning and data science was performed. People were more inclined towards C and Fortran, but then kind of NumPy made them come back to Python. So this saying I mentioned in the beginning of today's lecture, if you know NumPy really well, you are almost halfway through there in your journey of learning ML in Python. So this ND array, n-dimensional array, is one of the peculiarities of NumPy. We can make the calculations vectorized, so things can happen in parallel. Then broadcasting, I showed you one of the other advantages of NumPy. Every single element in an array can be multiplied with the scalar all at once. You can perform operations between arrays. If you want element-wise multiplication, you can do that really fast. If you want matrix-to-matrix multiplication, that also can be done very fast. So NumPy is really versatile. NumPy has its own inbuilt functions for implementing mathematical operations, as you saw, and you are basically getting the speed of C. NumPy is almost like a wrapper. What is undergoing in the background is C calculations, but NumPy makes it easy for the user to connect to those functions. So it's a very good library. In ML specifically, you will use NumPy pretty much all the time in data pre-processing, in data loading. If you want to do operations in data like feature transformation, or let's say normalizing a set of numbers. Let's say you have an image and you want to normalize the pixel values in the image, you can make use of NumPy. And if you have access to only CPU, then matrix multiplication can be done using NumPy. But of course, when you have GPU access, it's a completely different story. And of course, as I showed, vectorized calculation, calculating the metrics like accuracy, F1 score, or recall, precision. So NumPy is pretty much used in a lot of parts of the machine learning workflow. So in your current machine learning journey, of course, you are going to encounter NumPy in multiple places, but it has limitations. So you may have heard of a library in Python called as pandas. So in pandas, you can refer to different columns using their column titles, like column names. But in NumPy, it's not using those labels or names. It's using just the index. So this indexing might make it a bit less intuitive for beginners who are just starting their Python journey. So from a completely beginner point of view, maybe pandas is a little bit more intuitive because it's more like an English language. It's not indexing based, but I think for somebody who is slightly comfortable, even a little bit of Python experience, if you have, NumPy is very, very powerful. It's very easy to use. Also, there are issues when you have numbers like not a number, NaN, or none. It's you can't directly store that in NumPy. And as I mentioned already earlier, GPU acceleration is not there. If you, on the other hand, have TensorFlow data set, then you can leverage GPU parallel computation. So that is also one of the issues of NumPy. And this is, in my opinion, one of the main things which packages like TensorFlow did to revolutionize the growth of machine learning. So machine learning is what we see today in 2025 because of GPU computation, not because of CPU computation. But to make it happen, NumPy laid the foundations. So if we if we want to wrap up with a very interesting example, so let's do a mini challenge, right? Very simple. I think since you have already done the matrix multiplication and vector products, this should be very easy. But basically, we have 5 students and 3 subjects, and this should be like a 2-dimensional array. We can come up with some marks of the students out of 100. We want to calculate the average mark of each student, and we also have to identify top performing student. Okay, so let's create a NumPy array. So A equal to np dot array of, and then this should be list of lists, right? So inside the first list, there will be bunch of lists. So each list correspond to, let's say, how does it say in the problem? 5 students and 3 subjects. So for every student, there has to be 3 subjects and there has to be 5 students. So let's first create 5 empty lists inside this list. And why am I calling this list? Because if you just look at this part, that is list, but you are converting that into NumPy array. Okay. So now you have 5 students, and let's put the marks of 3 subjects. So 30, 70, and 95. Then 83, 68, 79. Then this guy has 92, 91, 40, let's say 39, 45, and 55. Actually, there are only 3 subjects. Then 90, 90, and 3. This guy scored very poorly in one of the subjects. This guy has 80, 81, 82. Okay, so these are the marks of 5 students. Okay, NP is not defined. Import. So the reason why this error occurred is because I had restarted the kernel, this runtime, because my browser was slowing down a lot. So I had to restart it. But let's import NumPy as NP. Oh, NP. So this should run now. Okay. Now what we want is we want the calculate the average marks for each student. Okay. So then what we can do is print np dot average mark should be mean of A along which axis? Along axis, along the rows. So axis 1, axis equal to 1. Let's see. So then you have 5 students, 1, 2, 3, and we could convert this into int. np dot int, or is it just int? Okay, first let me print it. So 65, 76, 58, 61, 81. So these are the average marks of these 5 students in 3 subjects. And identify the top performing student. Top performing student would be whoever has the maximum score, like maximum average score, because so this should be max of so maximum is 81, but we need to find the index, right? So what that means is where of okay, so what we have done here is, first of all, let me save this, right? Mean scores, mean underscore scores equal to np dot mean of this. This is fine. And let's say we are printing mean scores, but this has to be done after. Okay, so this is the mean score. Now what we want is, we want to see wherever mean scores in the mean scores array, where in whichever index you have the max. So where do you have the max of mean scores? you find the index of that. So here index is array of 4. So then this could be np.var. If it's a 2-dimensional array, you can do of 0 and then of 0. So then you get the index 4. So whichever student has index 4, that student has the highest score. Now, what if this guy had scored 100 in this exam, the first student? Then that student hopefully should have a higher average score. So then this number, this 4 should change to 0. Now, if we run the code, see, it has changed to 0. So now the student who has the maximum score is first 0th student. Now there are 3 subjects, right? Let's try to identify topper for each subject, subject-wise topper. How can we do that? So subject-wise topper is among the column, who has the highest score. So first let us find the highest score along the column. Subject top score equal to np.max of a comma axis equal to 0. So let me first not print this. So this is the subject wise top score. And then what we need is print. Okay, I'm already getting the suggestion. So, but I'll delete these two. So now subject wise top score I can get. For the first subject, 100 is the top score. Second subject, this 90 is the top score. Third subject, this 95 is the top score. Now we want to find which student scored highest in each of these subjects. So then what we can do is np.var subject top score equal to or rather a equal to subject top score. So a, let's see what happens here. np.var a equal to subject top score. So that should have for subject top score np.argmax of a comma axis equal to 0. So if we print this, we should have the indices of people with index of the people with the top score. So for the first subject, the person at 0th index has the top score. 0th index is this guy. Has he got the top score? Yes, he has 100 out of 100. For the second subject, whoever is at index 3 has the top score. So this is the student at index 0. This is at 1. So this is at 3. So he has 90, and 90 is indeed the top score for that second subject. For third subject, student at 0th index has the highest score, 95. So that is also true. So this is the student at the 0th index, right? So this is correct. We could actually apply the same thing here. So np dot argmax of mean scores. So mean score, we have mean of A. So np dot mean of A along axis equal to, we want to calculate the mean score, which means it should be along axis equal to 1, not through column. And then we want to find np dot argmax. So np dot argmax, but that too along which axis? Along axis equal to, along axis equal to, axis does not matter because it's only set of numbers. So this guy, since he has scored 100, this is the, and if instead of mean, if this is sum, then also it will be true, because whoever has the highest mean score has also the total highest score, because everyone is taking only 3 subjects. Everyone is taking the equal number of subjects. So np.argmax will give us the indices of those arrays, indices of this array, where we are doing np.sum of array A along axis equal to 1. So array A is this, axis equal to 1 means row. So for every row, we are calculating the mean value or sum depending on whether this is sum or mean. So sum of these three numbers, sum of these three numbers, sum of these three, like that. So for every student, 3 subjects, so we are calculating the sum, and this will find out the location where you have the maximum value. So if this was, let's say 60 or something, then first this student will not be the topper. This where is the topper? I guess this guy will be the topper, whoever is at the 4th index, so he will be the topper. And you can see that in the subject toppers also. Now the subject topper for the first subject is 0, 1, 2, this guy, whoever is at the 2nd index. So that is why you see the subject topper here. We can write here subject toppers equal to then here we can say overall topper equal to is student, then here we can just add a +1 student number, so that index is not counted as 0. So subject toppers are these. So now here we can print overall topper is student number, this comma np.argmax. Yeah, so this is now the mean score. So let me not print it. Mean scores are 75, 76, 58, 61, 61, etc. And subject top score, subject wise top score 91, 90, 95. So student number 3, who has index 2, has scored highest in the first subject. Student whose index is 3, which means student number 4, has scored highest in second subject. Student whose index is 0 has scored highest in the third subject. But the overall topper, although the student number 5 has not topped in any individual subject, that student is the overall topper, because that is student number 5. And why does it show 5 not 4? Because I have added a +1 here. If I remove this, this will be 4. You see, so this is the mini NP challenge. I mean, it's very simple exercise, nothing so fancy, but if you can do this yourself, you will get a decent command over using NumPy for arrays. There are so many inbuilt functions. So here itself, if you look at it, we used np.mean, np.array, np.sum, np.argmax, np.where. We used that before. So there are so many inbuilt functions. Today's lecture, we also use np.square root, np.log, np.random. All of these we use, right? So NumPy has a lot of inbuilt functions to make your life easy. But that brings us to the end of this lecture. I hope you really enjoyed this lecture, and I also hope you tried out these exercises along with me or right after this lecture. So doing is more impactful than just watching. So I highly recommend you to do this yourself. Open Google Colab, blank notebook, just write it yourself. Define these challenges for yourself and play with it. I'm sure you will come across some issues, you will make mistakes, but spend some 1 hour, 2 hours, you will feel very comfortable with NumPy. So thank you so much. We will meet again in another lecture with programming foundations for machine learning. We will look at other important libraries in Python, which will make machine learning much better, machine learning pipeline much better for you. Take care until then. See you. Bye.